Hello again. In this video, we're gonna look at independent random variables when you're considering more than one random variable at once. We saw in 6.1 the joint distributions of random variables. We looked at the joint CDF, the joint probability mass function, or the joint probability density function. We also looked at relations between the joint function values and the individual random variable functions. So for example, we saw the relation between the joint probability density function of x and y with the probability density function of x and so on. Okay, so we're gonna now look further at multiple variables at once, and we're going to look at independent random variables. Okay, so let's remind ourselves about when two events are independent. You say two events, E and F are independent when? We say two events are independent when the probability of the intersection is the product of the probability, right? So we can talk about independence of events. Okay, so now what about random variables? So we say two random variables x and y are independent if for any two sets any two subsets of R, so any two sets, you have the probability of x in A intersect y in B is equal to the probability of x in A times the probability of y in B. Okay, and this should hold for any subsets A and B. So it's not just enough to find one pair of sets where you have probability x in the one set intersect y in the other set is given by this product. You need it to hold for all subsets of R. Okay, another way you could phrase this using events like we did before is let E sub A be the event that x is in A. Okay, and let F sub B be the event that y is in B. Okay, and then we have the above statement is the probability of EA intersect FB should equal probability of, actually no comma over here, probability of EA times the probability of FB. And this should hold for all A subset of R and B subset of R. Okay, so for any two sets A and B, the probability x in A intersect y in B should equal the probability of x in A times the probability of y in B. And then you say that the two random variables are independent. Okay. All right. So a few trivial consequences of this. So for example, if you're looking at f of A, comma B. Okay, so F is the joint CDF of x comma y. Okay. Then what is f of A comma B? That is the probability x less than or equal to A intersect y less than or equal to B. And then if x, okay, so I will rewrite that. That is equal to the probability that x is in the set minus infinity to A and y is in the set minus infinity to B. Okay, So this is just like what we have above in the statement. Probability X is in some set capital A, Y, and Y is in some set capital B. You can think of this as a set capital A, think of this as a set capital B. And if X and Y are independent, then what will this be? This will be the probability X is in negative infinity to A times the probability Y is in negative infinity to B. Correct? And that, what is this? This is just the probability X less than or equal to A times the probability, and that is just the probability Y less than or equal to B. So you can rewrite this as F sub X of A times F sub Y of B. Okay? So that's a nice thing. When X and Y are independent, you have that F of AB is equal to F sub X of A times F sub Y of B. Okay? And you can say that if this holds, then X and Y are independent. All right? So this is just, you can think of this as a definition in terms of the joint distribution function. Okay? And now let's discuss what this implies in terms of the probability mass function or the probability density function. So let's look at the joint probability mass function of X and Y, P of X, Y. That's the probability X equals little x, comma, Y equals little y. Okay, so you can think of X being the singleton set and Y being the singleton set. So if you want, call it like this. Okay, and that's an intersection again, and if X and Y are independent, this will be the probability X in that singleton times the probability Y is in that singleton, which exactly is the probability X equals that X and the probability Y equals that Y. Oops, sorry. Okay, and so you have that the probability mass function is the product of the probability, the joint probability mass function is the product of the probability mass functions. Okay, and it also goes the other way. If you have the probability mass function equaling the product, then you do have that X and Y are independent. All right, and now in terms of the continuous case, in terms of the continuous case, what you have is a condition in the continuous case, the condition of independence, just as you would have guessed, what is this? Is equivalent to the joint probability density function f of x comma y being equal to f sub x of x, that's the density of x, or if you want to call it marginal density of x. The only reason they're using marginal is because of the presence of this joint density, and times f sub y of y, which is the density of y. Okay, so independence in the continuous case is the same as this. If you have this, you can conclude that for all sets A and B, probability x in A intersect y in B is the probability x is in A times the probability y is in B. And you could also conclude this exact statement. These are all equivalent. Okay, so before we've looked at independence as probability of intersection of events. Now we've just kind of tweaked that a little bit to talk about independence of random variables. And over here we need that for all sets A and B of that are subsets of the real line. You have the probability x in A intersect y in B is the probability of x is in A times the probability of y in B. Okay, so this needs to be true for all A and B that are subsets of the real line. Okay, and also this statement f of A B equals this statement right here, the CDF. The CDF is the product of the individual CDFs. That needs to be true for all A and B. Then you can say they're independent. So all these equivalent statements, f of A B equals f sub x of A times f sub y of B, and you have down here for the continuous case f of xy equals f sub x of x times f sub y of y. This should be true for all A and B, for all little x and y. All of these should hold, okay? So let me just throw that in here. So for any A comma B in R, you have this. And over here, for all x comma y in R over here, and also I will write over here for all x comma y in R. Okay, so there you go. You have what independence looks like in terms of the CDF as well as the probability mass function or the probability density function, and also the basic definition. Okay, so let's use this and try and look at some of these examples. Okay, so the first, and I'm going to follow the book examples. I'm going to do 2A, B, C, and then we'll jump to proposition 2.1. All right, so first let's look at example 2A. What is example 2A? So what you're doing over here is you're having a total of n plus m independent trials. All right, so you have n plus m independent trials. And each trial has a probability of success being P, the same. Okay. And you perform these n plus m independent trials. Now, x is the number of successes you see in the first n trials. And y is the number of successes you see in the next m trials. Okay. And as you would have guessed, since each trial is independent of the other, you would think that x and y should be independent, where you're counting the number of successes. So let's say you have n trials done, and these are m trials, and you look at x's number of successes here, and over here y is number of successes. Since each trial is independent of any other, you would expect that x and y are independent, but that's what we're going to rigorously prove. And the question says is, okay, so let's take a look at this. All right. So the probability of x equaling x and y are both discrete random variables. So we look at probability mass function. The probability x equals x intersect y equals y. Okay, what is that? Well, you want x successes in the first n trials. Well, that's just binomial for that. So n choose x. It doesn't matter what happens later. You're just looking, you stopped over there and are just counting the number of successes. So n choose x, p to the x, 1 minus p to the n minus x. Okay, after that you done with x. And now you're starting a new counter. After the n trials, you're starting a new counter and you're counting the number of successes in the following m trials. And what's the probability that equals y? It is m, choose y, p to the y, 1 minus p to the m minus y. Okay? And you know, of course, that this is the probability that random variable x equals x, and this is the probability that the random variable y equals y. All right. I mean, this is kind of a trivial example because already we know that each trial is independent of the other. Okay, so over here we're using the first n trials does not affect, we're showing that the results in the first n trials does not affect whatever happens in the following m trials. Okay. However, now if you take z to be the total number of successes, then you will have that x and z are not independent and y and z are not independent. Oops. Okay. You can try and play around with that and see. You look at probability x equals little x, capital Z equals little z, and even intuitively, clearly, you do know that. Okay. All right. So that's example 2a. So now let's do something a little bit more involved. Example 2b, what we have over here is, let me just read this out. Suppose that the number of people who enter a post office on a given day is a Poisson random variable with parameter lambda. Show that if each person who enters the post office is male with probability p and female with probability 1 minus p, then the number of males and females entering the post office are independent Poisson random variables with parameter lambda p and lambda 1 minus p respectively. Okay, so what do you have? You have that the number of people entering the post office this is Poisson random variable with parameter lambda. Okay, and let x be the number of males entering the post office. And y equals number of females entering the post office. What you want to show is that x and y are in fact independent random variables, and each one of them is a Poisson random variable with parameters lambda p for x and lambda times 1 minus p for y. Okay, let me just throw this in. A person entering is male with probability p and female with probability 1 minus p. Okay, so just throwing that in. So this is how I like to write down most of the data that you get when you read a problem. All right, so what do we need to do? We need to show that x probability of, so of course you're talking about number of males, number of females, so that's a discrete random variable. So let's look at the probability x equals I, y equals j. First we want to show this equals probability x equals I times the probability y equals j, and for each one of them we should show that you have a Poisson random variable. Okay, so let's write this down. What's the probability x equals I and y equals j? Well, we can write this using the total number of people. Okay, so this is the probability x equals I intersect y equals j, given x plus y equals I plus j times the probability x plus y equals I plus j, plus the probability x equals I intersect y equals j, given x plus y not equal to I plus j, times the probability x plus y not equal to I plus j. Okay, so what did we do here? This is just like, let's suppose you have that E is the event that x plus y equals I plus j. What did we do? We looked, and let's say A is the event x equals I intersect y equals j. Okay, so what did we do over here? We looked at probability. We want probability of A. We said this is probability of A intersect E plus the probability of A intersect E complement, which is the probability of A given E times the probability of E plus the probability of A given E complement times the probability of E complement. Okay, so that's all I've done over here. Okay, all right, so now take a look at this term over here. What's the probability x equals I and y equals j if the sum x plus y is not equal to I plus j? Well, that's impossible. So you know that this probability is 0. So this whole thing just reduces to probability x equals I intersect y equals j given x plus y equals I plus j times the probability x plus y equals I plus j. Okay? Because this term right after the sum sign is 0. Okay. So now let's try and find this. Okay. So what is the probability x plus y equals I plus j? Okay. Let's take a look at this. So I'm going to first just quickly look at that. What's the probability that the total number of males plus the total number of females is I plus j? That's the same as asking what's the probability that the total number of people who enter the post office is equal to I plus j. Correct? So how do we write that? What is this? That is a Poisson random variable with parameter lambda. So you know that that part will be e to the minus lambda, lambda to the I plus j divided by I plus j factorial. So that's just using the probability mass function for Poisson random variable. You remember probability, let's just call t a Poisson random variable. T equals k is e to the negative lambda, lambda to the k over k factorial. Okay, so just a reminder. Okay, so that is the second term. Now let's look at this first term. So what are you asking over there? What's the probability that I men come in and j women come in, given that there's I plus j total people? So what can you think of this as? You're given that the total number of people who entered is I plus j. So you're asking, what's the probability, given that information, that from these I plus j people, I of them are men? So now what is this? This will just be like a binomial random variable. And you're asking that for a binomial random variable with n equals I plus j, okay, and probability p, which is the same as the probability of being male, you're asking what's the probability this binomial random variable equals I. All right, you're asking let's just call a male entering success, and you're asking what's the probability that you have I successes. Okay, I'll write that better. Probability of I successes in this case. right? Does this make sense? So you know that I plus j people walked in, and you're asking, okay, here are I plus j people. What's the probability I of them are men? Okay, so what will that be? For binomial NP, you have n choose I, so it's I plus j choose I. P to the I, 1 minus P to the n minus I, which is I plus j minus I, so that's just j. All right, so that is this first part. Okay, so we can quickly, easily parse through this. So you have an I plus j over here. Okay, and I factorial, j factorial. So that's the I plus j, choose I. P to the I, 1 minus P to the j. I'm going to write that as e to the minus lambda P plus 1 minus P. Okay, that's just 1. So it's just lambda times 1. That's okay. Lambda raised to I plus j, I'm going to write it as lambda raised to I times lambda raised to j. And all over I plus j factorial. Okay, now what can you do? This cancels with this. And we want to show this is probability x equals I times probability x equals j, where you have Poisson random variable with parameter lambda p and parameter lambda times 1 minus p respectively. Okay, so what do you have? Let's just take a look. Let's combine this guy, p to the I, with lambda to the I. And we'll also separate this. So let me just actually first write down the whole product. You'll have p raised to I, 1 minus p raised to j. I'll have e to the, I'm going to split this exponential as e to the minus lambda p times e to the minus lambda times 1 minus p. Lambda raised to I, lambda raised to j, I factorial, j factorial. Okay, so now I'm going to underline things in two different ways. P to the I, e to the minus lambda p, lambda to the I factorial. I'm going to put these things together. 1 minus p to the j, e to the minus lambda times 1 minus p, lambda to the j, and j factorial. I'm going to put those together. Okay, so what do you have? You have lambda times p raised to I, okay, e to the minus lambda p over I factorial, all right, times e to the minus lambda times 1 minus p times lambda times 1 minus p raised to j, these are the zigzag underlined thing, divided by j factorial. Okay, so that's kind of nice. Now we have that the probability x equals I intersect y equals j is equal to what? If you look at what these are, this is exactly a Poisson random variable with parameter lambda p, the probability that that equals I. This is a Poisson random variable with parameter lambda times 1 minus p equaling j. Okay, so you can conclude this is the probability x equals I for a Poisson random variable, and this is the probability y equals j. Okay, and you have that x is Poisson with parameter lambda p, and y is Poisson with parameter lambda times 1 minus p. All right, so that's nice. If you have that jointly, you have a Poisson random variable and each individual success or occurrence is a certain type with a certain probability, then if you're just concentrating on the number of successes, even that will be Poisson. Okay, so that takes care of exercise example 2b. Okay, I this was just play with numbers, just rearranging terms and then discovering that what we do have is indeed Poisson times Poisson. Okay, so that was the end of 2b. And of course, you know, it goes unsaid. Any questions, please feel free to email. Now, let's look at 2c. All right. So what are we doing? Just reminding you, you know, in case you're getting, in case you've forgotten, because we just did this Poisson example, we're dealing with independence of random variables. All right. So now let's look at a different kind of distribution. A man and a woman decide to meet at a certain location. If each of them independently arrives at a time uniformly distributed between 12 noon and 1 p.m., well, this is a big window, find the probability that the first to arrive has to wait longer than 10 minutes. Okay. So, if you try and think of this separately as, oh, when does X arrive? I mean, when does the man arrive, and then when does the female arrive, and then what if the man arrives first, and try and break it up in those simple terms, that can get very messy and crazy. Instead, what you need to do is think of the arrival time as a point in R2, okay? And what the point is, one of the coordinates you'll call the man's arrival time, one of the coordinates you'll call as the woman's arrival time, okay? So, we need to set up notation. Okay, so let X, and of course, just like the example you had for a bus arriving and a person coming to the bus stop, we didn't just look at, we need to make random variables be numbers. We cannot have them be times. So it's easiest to just adjust it and let X be equal to the number of minutes, or the past 12, when the man arrives. So what do you know? X is uniform 0, 60, correct? And similarly with Y is the number of minutes past 12 when the woman arrives. And Y is uniform 0, 60. Okay. All right. And I like to draw a picture. I know in the book they're just going straight into the theory and explaining this without any drawing, but I like to do this. Okay, so that's the y-axis and that's the x-axis, okay? And that's 60, 0, 0, 60. All right, so this will stand for the woman's arrival time. That stands for the man's arrival time. Okay, so you know that is the line x equals y. Okay, and if you think about this, you're asking what's the probability that the person who arrives first, or maybe we can rephrase it like that, the person who arrives second arrives more than 10 minutes after the first person's arrival. Okay, so let's just look at it in this picture. So in this bottom triangle, what do you have? X is bigger than Y. So in the bottom triangle, you have that the man arrives after the woman. Okay, so over here, they both arrive on that dotted line. They both arrive at the same time. That has probability 0 because it's just a one-dimensional line, but still. Okay, so that is x equals y. We want to know, what if x arrived more than 10 minutes after y? So let's look at x equals y plus 10. So this line over here is x equals y plus 10. Okay. Similarly, let's look at y. Let's suppose the man arrived first and the woman arrived later, and the woman arrived more than 10 minutes after the man. And let's look at the line y equals x plus 10. Okay. All right. Now, let's just look at this grid. So, let's pick any point over here, in here. Okay. What do you have? You have x and y in there. And looking at this, you know, whatever the y value was, the x value was greater. Okay, so the y value is the same as the y value of that point on that line. Okay, so that's the y value. And then what does the woman have to do? She has to wait and wait and wait that many minutes until the man arrives. Okay. But what do you know? These many minutes, that's less than 5 because less than 10 because that whole distance is 10. So if the woman had to wait exactly 10 minutes, that would be the arrival. That would be the coordinate of the arrival time of man and woman. But since the person's arriving at this x value, you know that the x value is, yes, it is greater than y, but the amount by which it is greater is less than 10. Okay, so with that analysis, you know if the coordinate point x comma y arrival time is in that region, then you know that neither of them has to wait more than 10 minutes. Okay, however, if the arrival time is in this dotted region or in this region with circles, what happens? If the arrival time is in this dotted region, it tells you that the woman has to wait more than 10 minutes. Okay? And if the arrival time is in this circular region, it tells you that the region with the little circles, it tells you that the man has to wait more than 10 minutes. Okay, so I'm going to show you one way of doing this, and then the book has, it's the same thing, but still, I like to look at this picture. Okay, and so, sorry, why shouldn't be over there? All right, so what are you asking? The probability that the first to arrive has to wait more than 10 minutes. I'm just going to draw this, that the probability that x comma y is in this union x comma y is in that. That is the probability that the person who arrives first has to wait more than 10 minutes. Okay. In symbols, we will look at it in a second. All right. So what do we have? That's a probability that x comma y is in that region, plus the probability x comma y is in that region. Okay. Now, what's the probability that x comma y is in a certain region? You have to look at, we have to integrate over that region the joint density of x and y. And you have to integrate over this region the joint density of x and y. Oops. Okay. Well, what is the joint density of x and y? You know that the arrival time of the man is uniform 060. The arrival time of the woman is uniform 060. Their arrival times are independent. You're told that each of them independently arrives. So you know that x and y are independent. And we've seen what happens when random variables are independent. So their joint density is equal to the product of the densities. Oops. Okay, so that's 1/60. That's the density, right? Because it's uniform 0 to 60 times 1 over 60. That's the joint density. Okay, so that's quite nice. Now going back to the integral, so we have to integrate over that upper triangle 1 over 3600 dx dy plus the integral over the lower triangle 1 over 3600 dx dy. Both of these triangles are the same by symmetry, and you could use that as 2 over 3600 times the area of any one of them, because they're equal by symmetry. Okay, what's the area of any one? Well, you know that's 10, so this is 50. And so you have 2 over 3600, 1/2 base into height. Okay. And that turns out to be 25 over 36. All right. And what did they do in the book? It's exactly the same thing, and it's just without the use of a picture. By symmetry, they said the required probability is 2 times the probability that the arrival time of the woman is at least 10 plus the arrival time of the man. Okay, so then you can look in the picture at the region, and you know that is 2 times the double integral over the region x plus 10 less than y, f of x y dx dy. And you know that f of x y, they use the same reasoning to show that f of x y is 1 over 60 times 1 over 60, and proceed with this integral. All right, so if you want, here you go. So you have x plus 10 is less than y, so y is bigger than that, so it's that region. And how would you write that region without catering to this whole area thing? You know that y goes from 10 to 60. Okay, and for each fixed y, x goes from 0 to y minus 10. And f of x comma y is f sub x of x times f sub y of y, which you know is 1 over 60 times 1 over 60. And then doing this integral, you take that out, and what you'll have left is y minus 10 over here. And then you do that integral, and it turns out to be 25 over 36. So either ways, it's fine. It's really the same thing, but I just like to draw a picture to see what's going on. Okay, and yeah, I was a little bit lazy, and I just drew the triangle without writing down exactly what these points are. So here you go, that's 10, and that's y equals 10. This is x equals 10. Okay, so I hope these examples have shown to you how to deal with independence, at least on this case, in the case of just having 2 random variables, which is mostly what you will see, just 2 random variables. You will rarely have to do any kind of a triple integral, and how to use independence to get the joint density or the joint mass function and proceed with problems like this. Okay, so the example 2D is quite a cute problem. I want you to look at it yourself. I'm not gonna do 2E, so 2D, read yourself, which you actually have already, as you're told to do. And what we're moving on to now is proposition 2.1. Okay, and this is Lafond's needle problem. Okay, so now let's move on to proposition 2.1. What does that say? It says that if you have random variables x and y, okay, and they're continuous. So continuous or discrete random variables are independent if and only if their joint density f of x, y is equal to some function of x times some function of y on the whole plane. Okay, it's possible that some of these functions are zero, but then the region, you need to write down the region properly as a rectangle and stuff. But in any case, we'll come to all those details later. But you should be able to write this down like this. And h of x could be non-zero from 3 to infinity and 0 to the left of 3. That's okay. That's what I was saying. Okay? Or it could be non-zero from 3 to 5 and 0 to the right of 5 and 0 to the left of 3. All that's fine. Okay. All right. So this is what this says. So it's independent if and only if the joint density is a product of the density. Now, before we go into any details over here, I will tell you in words, what does this mean? What this means is that the density that you have, that the joint density in the first place, okay, should be written down analytically. I mean, written down as a function of x times a function of y. Okay, I'm not right now not addressing the region. All right. And this is, so whenever f of x, y is not equal to 0, you should have that f of x, y equals a function of x times a function of y. Okay. And number 2, the region where f of x, y is not equal to 0. What should that region be? It should be a rectangle. Okay. I mean, actually, I shouldn't say it should be a rectangle. It should be a Cartesian product of sets. Okay. Should be a region that can be written as A cross B. Okay. What does that mean? That is the set of all points x comma y such that x is in A and y is in B. Okay. So, I mean, if it's just one region, it could be, for example, an infinite rectangle like this, or for that matter, it could be an infinite rectangle over here and an infinite rectangle over here. Okay, so it doesn't just need to be one infinite rectangle. It could be, or one rectangle. It could be a union of rectangles, but you need to be careful about how you write that. Okay, so it can be a region that's of this form, which is like a Cartesian product of A and B. So for example, if you take a look at this region, okay, so here's a region. Let's suppose that's 0, 3, 1. Okay, you can say this is a Cartesian product of 0, 1 and 0, 3. All right. However, if you look at that region and you also look at this region. Okay, now this looks like two rectangles. It's a union of two rectangles, but this set you cannot write as a Cartesian product. Okay, so let's suppose this is -2, -4, and let's say this is -1.5. All right, or -2.5. Let's do that. Okay, I just wanted numbers to be different. So what is this region? This region is 0, 1 cross 0, 3 union -2.5, 0 cross -2, -4. But this is not equal to some interval or some set cross any other set. Okay, I shouldn't use the letter S. Let's put a Q. Okay, so this is not a Cartesian product. For a Cartesian product, you must have that. This is okay because here you could say this example, it's okay because here you have 1 to 3, for example, and you have -2 to -4. Here you can say you have 1, 3 union -2, 4 cross 0 to infinity. You see that? It doesn't matter. It doesn't have to be closed or open. The endings doesn't matter. So over here, you can describe this as a Cartesian product of sets. In this case, you cannot. So that is not okay. You need that the region is a Cartesian product of sets. Most of the examples we see will just have one set like this or like this. We generally do not have unions. But I'm just saying if you do have a union, it needs to be a union of this form. Okay? All right. So if you needed to put it in a very compact, succinct way, then what we have above is how you have it. Two random variables are said to be independent, if and only if you can write down the joint density as a product of densities on the whole plane. Okay, so I'm not gonna cover the proof of this. You can look at the proof of it in the book. It's pretty well given to you. Okay, and if you have any questions when you're reading the proof, of course, please let us know. All right, so let's look at example 2F. Okay, so what you're told is the joint density of x and y is given by f of xy equals 6e to the -2x, e to the -3y for x between 0 and infinity and for y between 0 and infinity. Okay, so, and we should always talk about the density function either on the whole real line or the whole plane, depending on whether you're talking about one or two variables. So you have to say, you don't just say what's happening to the density when it's non-zero. You also have to explicitly say that it's zero otherwise. Okay, and so over here we need to explain this. All right, so you have this as the joint density. Okay, so what can I write it down as? I can say that okay, so is this our functions x and y independent? Well, let I sub x be equal to 1 if x is between 0 and infinity and 0 otherwise. Let I sub y be 1 when y is between 0 and infinity and 0 otherwise. Okay, so this is just some function of x and y. I mean, this is a function of x, or actually let me just write. Okay, it's the same function over here. So I is a function that's 0 if you're 0 or negative, and it's 1 if you're positive. Okay, then what can you write down? You can write down f of xy equals 6 times e to the negative 2x times I of x. Okay, you can call this h of x. And it is e to the negative 3y times I of y. Call this g of y. This is a function of x alone. This is a function of y alone. And now you have this that you can write down the range as x going from 0 to infinity, x going from negative infinity to infinity, and y going from negative infinity to infinity. I have defined f of x, y as one compact function where you have a product of a function of x and a function of y on the whole region by using these indicators variables. I mean, in this case, the indicator is the same for both of them. You need not have had that the x and y have the same restrictions of between 0 and infinity. Okay, so you can see that x and y are independent. All right, so now what if you have x and y having the joint density being f of xy is 24x times y, where x is between 0 and 1, y is between 0 and 1, and x plus y is between 0 and 1. Okay, now you know from what I said before that this region is in fact not going to be a triangle, right? What is this? I mean a rectangle. This region is the inside of that set. Okay, so that itself tells you it's not going to be independent. And also, you know, so if you pick any x, well, y only can be in that little range. If you pick any y, x can only be in that little range. So you know that what x can be depends on what your y value is. Okay? Anyway, so that was a very loosey-goosey explanation of what you have. But you know that no matter what you do, you cannot write down this function as a product of, even if you just use some indicator variable. So let's say I of xy is 1 if x comma y is, or maybe I'll just write this, if x is between 0 and 1, y is between 0 and 1, and x plus y is between 0 and 1. But now you do have that f of xy equals 24xy times I of xy on the whole plane. Okay. However, you cannot write I of xy as a function of x times a function of y. There shouldn't be any parentheses here. It's just 24x times y. Okay, so then you know that x and y are not independent. Okay. All right. So this is just demonstrating, look, in one case we can write it down as a product because the region is a Cartesian product of subset of the subset of the x-axis times subset of the y-axis. Okay, now let's just talk about generality. Suppose you have n random variables, x1 through xn. We say n random variables x1 through xn are independent if for any n subsets of the real line the probability of x1 in A1 intersect x2 in A2 ... intersect xn in an is the product of the probabilities. Okay, and the I don't know if you've seen this product notation for summation. Okay, so just like you had summation, this is now the product equivalent to summation. Okay, so that's true for n random variables. It's just a generalization for the 2 random variable case. And how about if you have infinitely many random variables? If you have infinitely many random variables, you say that they are independent if any finite subcollection is independent. All right, so let me just write that. We say an infinite collection of random variables if and in fact this infinite collection could also be uncountable, and that's what you see often in processes. You have processes are indexed by time, so x sub t is the process for time t, x sub k, not k, x sub r is a process for time r, and you often have these processes, and x sub r is independent of x sub t for all r and t, or but you also have that you can consider more than 2 random variables, x sub r and x sub s. So in processes, you often have this notion of independence where you're looking at every finite subcollection is independent. Okay, so we say an infinite collection of random variables is independent if every finite subcollection is independent. Okay. You see this in processes, like I said. Okay. So let's just do one more example. And the reason I want to do this example is because it's the first example we're looking at where we're seeing 3 random variables at once instead of just 2. Okay. So let's see that. So you have that is example 2H. Let's x, y, and z be independent random variables. And they're all uniformly distributed over 0, 1. Find the probability that x is bigger than or equal to y times z. Okay. So take a moment and think about what is their joint density. What is f of x comma y comma z? We know that they're independent, so the density is equal to the product of their densities. Okay. The upside down therefore is because. Okay. And what is this? That is 1 times 1 times 1 if x is between 0 and 1, and y is between 0 and 1, and z is between 0 and 1. So this density is 1 when you have that, and it is 0 otherwise. Okay, so it's 1 on this 3-dimensional cube, and it's 0 outside of that cube. Okay, so what is the probability that x is bigger than or equal to yz? Okay, so there's no restriction on yz. Yz can be anything. Okay, in this cube, yz is anything. And now, what is the probability that x is bigger than or equal to their product? Okay, so how do you do that? You remember from Calc 3, okay, first let's write it down. X bigger than or equal to yz of the joint density. Okay, well, you know we already found out that that's 1 on that cube. All right, so what does this integral translate to? Z can be anything from 0 to 1. Y can be anything from 0 to 1. What does x need to be? X needs to be anything from yz to 1 because it's bigger than or equal to yz. And this is just 1 dx dy dz. Okay, so let's do this integral 0 to 1. Integral 0 to 1. What's the integral of 1? You'll have x evaluated from yz to 1 dy dz. So that is integral 0 to 1. Integral 0 to 1. 1 minus yz dy dz. Okay, and so integral 0 to 1, let's do this inside. And what do you have? Y minus y squared over 2z going from 0 to 1 dz. That's integral 0 to 1. 1 minus z over 2, right? And that is z minus z squared over 4 going from 0 to 1. So that's 1 minus 1/4. And the answer is 3/4. Okay. So this was, oh, I already wrote that. That's above. Example 2H. And I just wanted to demonstrate to you that, you know, for 3 variables, it's not very different. You just will have a triple integral when you're doing calculations. Okay. So that brings us to the end of section 2, 6.2. There's more examples in the book. There's 2I, which is the probabilistic interpretation of half-life, and another example, 2J. It would be nice if you looked at these examples. And also, example 2G, what this shows you is how a computer can choose a random subset. It's just very, very long and involved example, and you can look at those on your own time. Okay? All right. Well, I hope all that made sense to you. And to summarize, what do we have? We have random variables, 2 random variables. Let's say you have 2 random variables. You say that they're independent if for any set A and B, the probability X in A intersect the probability Y in B is the product of the probability X in A times the probability of Y in B. Okay? It also turns out that the joint CDF is a product of the CDFs, individual CDFs. It turns out that the joint mass function is a product of the mass functions, individual mass functions. It turns out that the joint probability density function is the product of the individual density functions, which we're calling the marginal density functions. Okay, so that summarizes everything. This kind of independence you often use to find the joint density of something because you know the individual densities, you know their independence, so you know that the joint density is a product. Okay, all right, guys. Well, that's the end of that. And I hope you're still awake and listening to this. And have a nice day. Bye.